Hello everybody, we are in week 5 of this particular course. In this week we shall look at number system and arithmetic building blocks. Today's class we shall cover some of these concepts, basic number system, fundamentals of number systems, binary to decimal and decimal to binary conversion, octal and hexadecimal representation, and we shall also have a quick look at fixed point and floating point representation. So, before that a quick recap of what we discussed in week 4. So, we looked at logic circuits, important logic circuits like a multiplexer which steers one of the many inputs to the output based on certain control inputs. We looked at demultiplexer which does the reverse operation. So, if there are a number of outputs and one input need to be steered towards that based on what is presented at the control input or the selection input, the data input is steered towards one of the data output terminal. So, that is what we had seen for demultiplexer operation. And we also saw that demultiplexer circuit and decoder circuit are essentially same. So, decoder decodes a particular combinations or input bit pattern when it is present at the input side, and decoder essentially generates all the minterms, and these minterms can be combined together with OR gates to produce many different kind of output. So, whenever we are talking about multiple output generation, then decoder OR combinations. So, multiple OR gates which takes appropriate minterms from the decoder output, that can be useful. And we also saw encoder. Encoder is reverse of decoding operation, where input signal is encoded in certain number of bits, and in priority encoder, if number of inputs are active simultaneously, then according to the priority assigned, one of the input gets encoded to the output. And we also looked at parity generation and checking using XOR gate, and we found that it is useful for correcting detecting one bit error in the transmission or in the bit pattern. So, to discuss number system, first we look at one example of an odometer which we have perhaps all of us have seen, those who drive vehicle, or we have seen how the meter which takes note of the distance in the vehicle is showing the increments in the number. So, we have seen that if 1 unit distance is travelled, say 1 kilometer distance is travelled, so the number gets increased by 1 unit over here, okay, and then next unit and it gets incremented. So, when all it is in decimal system, so when it completes 0 to 9, then next digit over here, say this one, will get incremented. Okay. So, that is what we have already observed. So, in decimal systems, if you look at the way the digits are presented, so 0, 1, 2, 3, okay. So, these are the valid digits up to 9. After that comes 0 in this unit place, and in the decimal place, in the tens place, 1 comes into the place. Okay. So, this is how decimal odometer works. So, if we consider instead of 10 digits decimal systems, we had octal systems, that means only 8 digits are available, and let us number them, let us consider the representation of them is 0 to 7. So, what would have been the case here? So, up 1 unit distance travelled, it goes from 0 to 1, which is fine, then 2 unit goes from 1 to 2, but when it goes up to 7 unit, which is there in the representation 0 to 7, after that when it travels one more unit, 1 more kilometer, what will happen? 8 is not available, it is an octal system, 0 to 7 is only available. So, at that time what will happen? The second place over here, okay, 8th place, so we will say that it is 8th place. If earlier one was 10th place, this is 8th place. that gets incremented by 1 from 0 to 1, and over here it comes 0. So, the meaning here, this 1 0 and this 1 0 is different. This 1 0 is 10, 9, after that 1 more unit. Here 7, after that 1 more unit. So, this is 8. Is it clear? So, if we talk about binary system, in the digital circuit, digital system, we are talking about binary, zeros and ones switched on or switched off. This is the way we are looking at it. So, a binary system base is 2. Okay. So, 0, after that 1 unit travelled, so it is 1. So, after 1, another unit is when it is travelled, what will happen? 2 is not available as a digit. So, this 2's place, now we will call it 2's place, right, 10's place, 8's place, now the second place is 2's place. So, 2's place will get incremented by 1 and 0 will come over here. Okay. So, this 1 0 over here is 1 plus 1, which is 2, and this way it will continue. And if you look at this incrementing the next higher position place, okay, then at 0 0 1 0, which is decimal 10, for that in octal we will be having, this is your 8 1 0, then 9 is 1 1, this is 1 2. Okay, that is in octal. And in binary system, if we go on incrementing the way we have incremented the earlier cases one by one, we will see that it is 1 0 1 0. Okay. Now, earlier we was talking about 1's place, 10's place, 8's place, 2's place, that is the second position. So, the number appearing at units place and the number appearing at the second place in decimal, which is 10's place, in octal that is 8's place, and in binary it is 2's place. So, this place provides a different weightage, okay, different place value to that particular number. Okay. So, if we look at the number that is 1 0, so in decimal the 1 here is appearing at 10's place. So, 10 to the power 1 multiplied by 1, and this is 0, and it is 1's place, value is 1. So, 0 into 10 to the power 0. So, this is what actually it means in the amount. The amount here is this much. Over here, if it is in 8th octal system, it is 1 into 8 to the power 1 plus 0, and in binary system it is 1 into 2 to the power 1. So, that is what we have already seen. And by this we see, if we go on adding the place value over here 1 0 1 0. So, this is units place, this is 2's place, this is 4th place, and this is 8th place. Okay. So, then this actually goes into like this 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. So, 1 0 1 0, 1 into 2 to the power 3, 0 plus 0 into 2 to the power 2, 1 into 2 to the power 1, and 0 into 2 to the power 0. If we look at the odometer, the example that we had seen in the previous slide, this is how this, if you add them up, this is 8 plus 0 plus 2 plus 0. So, 10. So, it was decimal 10 equivalent that we had seen in the last row. Okay. Similarly, in octal, it is 1 into 8 to the power 1, that is 8, right, and 8 to the power 0 is 1, and 2 is a valid digit. So, 2 into 1 is 2. So, 8 plus 2, it was 10. So, the last row, that is how we had a equivalent of 10, decimal equivalent of 10 for representation 1 2 in octal and 1 0 1 0 in binary. Okay. So, this is the concept of place value. When we put it more formally, so this is what we would be able to see. So, if we have a number system with a base or radix r, okay, by which the allowable digit, valid digits are 0 1 2 3 up to r minus 1, for example, in octal system 0 to say 7, okay, in binary 0 and 1 only. Okay. So, then the number represented in this manner, where this is the point which divides the integer and fraction part. So, decimal point in decimal system, octal point in octal system, binary point in binary system. So, that is the point over here. Okay. Then its corresponding value is represented by, from the example that we had seen here, if we continue, that this is the way the value is arrived at. So, there are n plus 1 digit to the left of the decimal place, and that is the integer part, the decimal point or binary point or octal point, and then m digit towards the right. Okay. So, in that case dn into r to the power n, r is the base, plus dn minus 1 into r n to the power minus 1, that we will continue, right, up to d naught into r to the power 0, plus when it goes to the fractional side, what happens? So, d minus 1, this is the first digit, okay, which is multiplied by r to the power minus 1. So, the place value here is 1 upon r, right. So, this is we have to keep note of. The next place value is 1 upon r square. So, r to the power minus 2. So, this way it continues, and we arrive at the value by this manner. So, we are more interested in the binary representation. Most of our work will be using for the binary system. So, we elaborated it little bit more. So, here is a binary number, only 4 digits before the decimal binary point and 4 digit after it has been shown, and the corresponding weights you can see, which is written in these places. Okay. So, these are the corresponding weights. Okay. So, if we look at the this example 1010, which is 1010.101, what will be its value? So, 1010 we have already found out the integer part before, right, which is 10, and the fractional part, this is 1 into 2 to the power minus 1 plus 0 into 2 to the power minus 2 plus 1 into 2 to the power minus 3. Okay. So, then if you add them up, 0.5 and this is 0.125, 1 upon 8 is 0.125. So, it is 10.625, and this is the way number. So, this 2 means base 2 and this 10 means base 10. So, 1010.101 base 2 is equivalent to 10.625 in base 10. So, this is the way we can convert from binary to decimal. Okay. And some important this conversion, the integer part over here it is shown, which we keep in mind. So, only 1 is 2 to the power 0, it is 1, 10 is 2, 100 is 4, okay, 1000 is 8. So, this way these are some of the things that we will often encounter, and here we remember that this is 2 to the power 8. So, this is incorrect. So, when it is 2 to the power 8, okay, it is 256. So, when it is 2 to the power 10, so this is your 2 to the power 10. So, it is 1024. So, 1024 here also is represented as 1K. So, when we say 1 kilobit, right, it means 1024 number of bits. It does not mean 1000 bit, that is there in the decimal system. So, in binary or digital logic, digital representation of numbers, 1 kilo stands for 2 to the power 10, which is 1024. So, 2K represents 2 to the power 11. Okay. So, that is 2048. If you multiply, you can see that this is 2048. So, 2 to the power 20 is 1024 kilo, that is 1 mega. So 1 mega is represented in this manner. So that is what we take note of, and also that there will be, when we talk about 256, after 1 it is 2 to the power 8 zeros are there. Okay. And this is another thing we often come across. So 1 1 is 3, 3 1s are 7, 4 1s are 15. So if 8 1s are there, this is 255. So if you just increment by 1, the way we have seen the odometer, so after that what will be the next value? 1 0 0 0 0, 4 0 here and 4 0 0 0 0. So here the what will get incremented to 256. This is your 256. Okay. Now that was binary to decimal. If it is required that we have a decimal number, we want its binary equivalent, how do you do? Okay. So we do it by, let us first look at the integer part. So when we look at conversion of, say, integer part, say 10, so we first divide 10 by 2. Okay. Note the quotient and the remainder. So this quotient 5 comes over here, you see the color, So again we divide by 2, we note the quotient and the remainder. So earlier when 10 was divided by 2, 5, remainder was 0. This time when it is divided, remainder is 1. So these 2, again we divide by 2, right? This is 1 and remainder is 0, because it is completely divisible, 2 is completely divisible by 2. And then 1, again when we divide by 2, basically we get the quotient 0 and the remainder remains 1. Okay, so that is because only that the digit is less than 2, right? So whenever we reach here, there is no further scope, we stop this exercise. That means successive division by 2 of the original number and the quotient that it gets. And the remainders from bottom to top, the way it has been shown here, we take note of, with the first bottommost one is the MSB and topmost one is the LSB, that is 1010, that is the corresponding binary equivalent of the decimal. Okay. That is how we do the conversion for the integer part. And if we do the consider the fractional part, earlier it was division, here it is multiplication, right. So 0.625, if we consider the number we have seen before. So 0.625, first we multiply by 2. So what will be the result? 1.25. So 1.25, we look at the number which is the integer part of it, we call it carry, we keep it here, and the fractional part we keep it here. So 0.25, then we multiplied by 2 again, so we get 0.5. So there is no carry, so this is 0 and this is 0.5. And then 0.5 we multiply again with 2, we get 1 and this is 0. Okay. So when this is after that there is no further fractional part available. So this time we will go from top to bottom. So the topmost one is the MSB in the sense that comes after the binary point, and the bottommost point one is the LSB. So 0.625, its corresponding binary equivalent is 0.101. So this is the way decimal to binary conversion is done. Okay. So we have one more example here, 23.6. So here what we do, again we follow the same process. We divide the number into integer part and fractional part, and you keep on dividing it by 2 successively and get the quotients. The quotient again comes here, this quotient comes here, right, and we note down the remainder, and then we read from bottom to top. So it will come as 10111. So this part, this is what will come. And for the fractional part 0.6, we keep on doing the multiplication, right, and whenever there is a carry, that is value becomes more than 1, right, we note it here, and then we read it from top to bottom. And we see that when you come over here, it is not actually fractional part is not becoming 0, right. So, it will go on giving some value over here, right. So, but in practical cases you will be needing to truncate it because of some finite number of bits are available to you only, okay, in the realization. So, if it is truncated at 5 bits, okay. So, from top to bottom if we read then it is 10011, that is what we see here. So, if there are 6 bits, then another, if you do the multiplication, then whatever number comes, so that will be writing, you will write here 7 bits accordingly, it will be presented. Right. So, octal we had just seen in the discussion where we had seen the odometer. So, if in some case octal number based representation is required, okay, then we know the valid digits are 0 to 7. This is we have already discussed, and these are the corresponding weights or the place value. So, after octal point 8 to the power minus 1, 8 to the power minus 2, the one that I had said before. So, octal the valid digits are 0 to 7 only. So, consider a octal number 35.6. Okay. Then what is the corresponding binary? It is very easy to convert from octal to binary and binary to octal. So, what we need to do only, we form a group of 3, okay, because in octal it is 2 to the power 3, 8 is 2 to the power 3, right, binary is base 2, it is base 8. So, 3 we represent it in this manner, 5 we represent it by this is the octal point which becomes the binary point, and 6 is this one, right. So, first we represent in this manner, and after that the leading 0 before the binary point and the following 0 after the binary point we ignore, because that does not carry any sense. This is the corresponding binary equivalent. And if you have to convert from binary to octal, so this is the binary number. So, this is binary point is the reference point. So, from this binary point we keep forming group of 3. Okay. So, this is one group, this is another group, this is another group, okay, the integer part. And when you see that only one member is there, so you can put some leading zeros to make a group of 3. And after the regarding the fractional part, again this is the reference point. So, you form the a group of 3. Then again to form a group of 3, you do not have 3 digits, only one digit is there, you put some 2 succeeding zeros, a group of 3 is formed, right. And then for each of this group you represent the corresponding octal equivalent. So, 001 is 1, 101 is 5, 110 is 6, and 101 over here is 5, and 100 over is 4. Okay. So, this is the way from binary to octal conversion can be done. And there is another number system you may come across in the digital electronics discussion. So, that is called hexadecimal. So, hexadecimal has got a base 16, and 16 means then 0 to 15, some 16 digits will be there, but decimal numbers are up to 9. So, after that what is done, the capital letters A, B, C, D, E, F are used, okay, which is equivalent to 11, 12, 13, 14 and 15, right. And if you look at the number representation, the weights will be 16 to the power 0 over here, units place, 16 in the 16th place, second place, 16 square in the third place before the hexadecimal point, and 16 to the power minus 1 here, 16 to the power minus 2 after the hexadecimal point, it will go on, right. And the conversion is similar to octal system. Again, because it is 2 to the power 6, 2 to the power 4 is 16. So, we will be forming group of 4 binary digits. So, if 3D.6 is to be represented in binary, so 3 will be represented by 4 binary digits D. Okay. If you look at the corresponding value over here, it is, in the binary representation, this is 1 0 1 0, this is 1 0 1 1, this is 1 1 0 0, and D is 1 1 0 1. Okay. So, this is your D, right. So, and then 6 is 0 1 1 0 in 4 binary digits. So, again leading 0 and following zeros before and after the binary point you ignore, and then this is the corresponding number. And binary to hexadecimal conversion, again you will be forming group of 4 with starting from the binary point as reference. For integer part you will go towards left, and for fractional part you will go towards right. Keep forming groups, and if required you add some leading 0 or succeeding zeros, and then you convert it to corresponding hexadecimal, and the job is done. And to get decimal to binary conversion, decimal to binary conversion is already by integer power to the 8 to the power 1 2 3 etc., or 16 to the power 1 2 3. So that kind of multiplied with coefficients, and you add them up, you will get the corresponding decimal value. And decimal to octal, earlier you had done for binary it was division by 2 for the integer part, it will be division by 8 or 16 for the integer part, and for the fractional part it was multiplication by 2, it will be multiplication by 8 or 16. Okay, the method is similar. Having noted this, and also earlier that especially the fractional part you do not have all the number of bits that is required to get the kind of precision that you require. So, in actual practice you will be having a fixed number of bits available to represent a number. So, with this fixed number of bits in a presentation which is called the fixed point representation of number, the width, that is the number of bits, total number of bits available to represent the number, and the position of the binary points are defined. Okay. So, to give you an example, if the 8 bits stored in the memory is this 1001 1110, okay, and it is represented in fixed 8-3 representation. So, this is the understanding that these numbers stored in the memory are represented in this manner, right. Then of course, the width is 8, okay. So, 8 bits will be taken, and then binary point will be fixed at after the binary point there will be 3 digits. So, 110. So, this is the corresponding value in the decimal. If you just convert binary to decimal, this is what you get. So, instead if it was 84, so 4 digits would have been there. So, same 8 bits, because width remains the same, right. That is what we have mentioned here, the width to be 8. So, then what happens? So, this value becomes integer value becomes less, and the fractional part we have got more entries, and then if you add them up, this is 9.875, that what is you get in decimal equivalent. And instead if it was 82, it was 83, 84, this is 82. So, 2 digits will be there after the decimal, after the binary point, and again if you convert to binary to decimal, you get 39.5. Okay. So, the same number depending on the number system, the fixed point representation has different values. And one thing you note here, that by shifting this binary point, okay, if you are shifting it towards left from here, you are shifting it towards left, what has happened? The number has become divided by 2. You can see that this number 9.875 is half of this one, and if you shift it towards right, this was 0.110, this is 0.10, this is 39.5, it is multiplied by 2. So, if you shift 2 units, it will be 2 to the power 2, okay. That will come into picture. See, 2 units to the right, so it is multiplied by 2, and if it is 2 units to the left, it is divided by multiplied by 4, and if it is 2 units to the left, it is divided by 2 to the power 2, that is 4. Okay. And one good thing about this fixed point arithmetic is that integer arithmetic circuit can be easily used, because integer representation is just a special case of this, where there is no bit after the binary point. Okay. So, the last point, just to conclude, there is another representation called floating point representation. So, what we had seen in fixed point representation, that say 8 to 4. So, there are 4 digits after the binary point. So, the precision that is available is 2 to the power minus 4, that is 0.0625, and 8 3 digits. So, precision is 0.125. So, here the precision is better and here the precision is a bit less, but in doing that, what you see, the range over here is less compared to the range in the other case. And in fixed point representation, once we fixed the representation, precision is always fixed. Okay. So, this is what we have noted, and one simple formula to calculate the range is the number of bits that is before the binary point is A and after the binary point is B, then it is can be calculated in this manner. Okay. Right. So, now then came another representation, it is called floating point representation, where the binary point is not fixed. Binary point in the number, in the bits, it can move from left or to right. The idea is always we will be having in a normalized version a 1 present here, and rest is the number of which is after coming after the fraction. So, if the original number is say 1101.01, right, we shall shift the number, we have already noted the shift. So, we shall shift the number in such a manner the decimal point comes over here. So, normally only 1 will be present before the decimal point. Okay. So, this is the corresponding number. So, how many shifts are there? So, 3 shifts are there. So, 3 shifts means to the left. Okay. So, that means it is 2 to the power 3. So, this into 2 to the power 3 is same as this number, right. So, in floating point representation, we note this 3, the exponent, in the exponent part, and what is after this 1, that is 10101, so this part, right. So, that is noted in the mantissa part. So, we mention how many bits are reserved for exponent part, how many bits are reserved for mantissa part also. Okay. We have not discussed yet the negative number or the sign, that part will come later. So, here we are talking about the magnitude part only. So, the number will be represented in this form, m into 2 to the power e, m is the mantissa part, that is what is coming after the fractional point when a 1 is present just before the binary point, and the number of shifts that is required for which the exponent terms gets defined. Okay. So, this number will be stored in the memory, okay, in the floating point representation by this convention is as 011. 011 is the exponent, that is 3 over here, and the fractional part with 1 in the left hand side, 10101. So, that is what it will that is how it will be stored in the memory. So, that is the floating point representation. Here the gap between consecutive number is high for larger numbers and small for smaller numbers. So, precision is not fixed. Okay. So, we shall mostly discuss with deal with fixed point representation in our subsequent discussion later. So, to quickly conclude, number system with base r base or radix r has digits 0 to r minus 1. Place value or weight is multiplied with the digit to find its contribution. Okay. So, if it is multiplied with 0, then there is no contribution. To convert decimal to binary, integer is successively divided by 2 and remainders accumulated, and for converting the fraction, it is successively multiplied by 2 and carry is accumulated. And for octal and hexadecimal system, the process is similar for the conversion, but instead of 2, we are using 8 or 16 for octal and hexadecimal respectively. And octal hexadecimal to binary relationship, I mean to and from, it considers grouping of 3 or 4 binary digits. And fixed point representation has fixed precision. Fixed point arithmetic is similar to integer arithmetic, and we shall discuss elaborately that part later. And floating point representation has variable precision, and gap between number is higher for larger numbers. Thank you.